This video goes from beyond our simple introductory definition of a bond to what is really the source of attraction in a bond. So when we talk about gaining and losing and sharing, that is important because that defines what type of compound we have. But for all compounds, it's about the attraction within a molecule, the intramolecular force, and what that does to the stability or to the potential energy. So Coulomb's law is normally considered a physics law, but really just any scientific law that gives us the relationship for a force of attraction. There's an equation you can use to actually calculate values, but for our purpose, it's much more important just to conceptually understand what's going on. So Coulomb's law says the attraction between particles, and we would be talking about particles within a molecule or compound, is proportional to, we're not going to do any calculations, the size of the charge, which is related to maybe the charge of an ion or the charge of protons and electrons. So the charge things that are attracting or repelling each other, protons and electrons, and then the distance between them, but that distance squared. So we're directly proportional to the charge, we're inversely proportional to the square of the distance in terms of attraction. Since we aren't doing exact calculations here, we just need to think about are our charges big or small, and is our distance big or small? So as it says, the magnitude is based upon how many protons we have in our nucleus. Elements that have more protons have a higher value for that Q, for the positive part of that attraction. The negative part is the negative thing, either how many electrons we are sharing in covalent or metallic bonds, or the charge of our anion in an ionic bond. So we can compare how many protons are attracting how many electrons, what charge of cation is holding on to what charge of anion. The R, the distance, is based upon how big the atom is. So it's very important to know that all of this still comes back to periodic trends: electronegativity, ionization energy, electron affinity, but maybe more specifically Zeph in terms of my positive charge, and shielding in terms of my distance. So the more Zeph I have, the bigger my force of attraction can be because of more protons. The more shielding I have, that's a bigger R, which would then make my force of attraction become smaller. So as I move up and down the periodic table or left and right, I can make predictions and use that to do explanations. Sometimes, instead of being shown just in terms of mathematics or the elements, we show this with a graph. This is a very common graph that has started to appear in multiple choice and can even transition to a free response question. It shows the potential energy between two atoms relative to the distance between them. This is normally shown for covalent compounds, but we can make similar graphs for ionic as well. So the distance is how close our two atoms are. So we could have them very far apart, very close, or almost on top of one another. And then potential energy is how stable has it become. Low potential energy is the most stable an atom, or in this case, a molecule could be. So if our distance is huge, so if there's no interaction, the atoms aren't touching or aren't attracting each other at all, that's when we describe it as having no bond. They aren't attracted, they aren't bonded, and there is no change in potential energy for those. As they come closer together, the reason they come closer together is there's an attraction between them. That attraction releases energy or lowers our potential energy. The lowest point here is the distance at which they are most stable, the distance where there is some overlap and we have the most attraction. Here it says some attraction. Really, I would describe here as some attraction, here as some attraction. Right there is our maximum attraction, that bottom point. But if we get closer and closer together, we see that this increases. we would have a vertical asymptote here because we can't have the atoms perfectly on top of one another. But if they get super close, then the electrons from each atom repel one another. The nuclei from each atom are so close they repel each other that they actually would come right back apart. They are too close to stay together. So when I compare my x-axis, that's telling me about how big my atoms or how long my bond is. When I compare my y-axis, that is telling me how much more stable is something becoming. So the deeper down it goes in terms of potential energy, that's an even more stable bond. This simulation we might play with a little bit in class, but is a great example of this, where you're just playing with different atoms and you can see where they fall in terms of the most stable bond. When we are describing this, that place right there is considered the bond length. Atoms and molecules, we have an electron cloud that's hard to describe the probability of exactly where anything is. So when we're talking about how far apart atoms are, we're looking at average distances here. So the average distance of two atoms that are bonded is considered the bond length, because we probably have some wiggle in and out there as electrons move around, depending on our polarity and our electronegativity difference. But it's that lowest place or the most stable place that they can be that is the place that strongest bond, and therefore the bond length. The shorter that distance, that's a smaller R value as we go to Coulomb's law, that's going to lead to a larger force of attraction. So shorter bonds tend to be stronger, and we can summarize this here. Small atoms have short, strong bonds compared to large atoms. So when two things from near the top of the periodic table are bonded, they're likely to have a stronger bond than two things from near the bottom. The more electrons or the more charge we have within our bond, the stronger it tends to be. Once again, coming up here, if I was sharing a carbon to carbon bond, maybe, if there was two electrons in the middle, I would have a certain number of protons attracting those two shared electrons. If it were a double bond, I'd have 4 electrons in the middle. I'd still have the same number of protons, but attracting more electrons. Q2 would be larger. The force of attraction would be larger. So that would pull that bond a little bit closer together because of a larger force of attraction, and it would make that bond stronger as well. So small atoms have short, strong bonds. Double and triple bonds tend to be shorter and stronger. So that's all described here. And some other terms that connect with this. Bond order is a term that we use to kind of simplify the idea of single, double, or triple. A bond order of 1 is single, 2 is double, or 3 is triple. Just another phrase for that, because we'll see how we could also think about average bond orders. And then bond energy was alluded to in the first video. It's how much energy is needed to break the bond. Basically, it is taking our bonded atoms and moving them back up here. How much energy do I need to put in to make that happen? And if we look at this, this may look familiar with the graph we've seen in the past, and we'll see again about the start of a chemical reaction, where we are taking bonded compounds and breaking them apart throughout the reaction process, putting energy in, raising the potential energy to separate them and start a bond.